Okay, so hello everyone. Welcome to the problem solving sessions for Introduction to Automata, Languages and Computation. So this week we will be looking into grammars. So we defined. Okay. So we defined what is called CFG, which is context-free grammar. Okay, so we defined what is called CFG. How did we define that? It was a set of 4 tuples. So you had a start state, we had a set of productions, we have a set of variables, and a set of terminals. So terminals would be your strings A, B, C, and so on, or something, and variables would be the non-terminals, which would be letters like this, and productions would be something like A gives B, C, and A, B, and so on. And there would be like lots of rules. So you have a bunch of rules, and then you have a special symbol. You have a special non-terminal, which is the start symbol. So you start your grammar from a certain start symbol. That's how we define. And we looked at what is called a parse tree and derivations. So today what we are going to do is we will look at two different kinds of derivations. One is called leftmost derivation, and the other is called rightmost derivation. Okay, then we will see what is called ambiguous grammar. And in that case, how to make it unambiguous, or can we make it unambiguous? And we will also see certain rules to simplify. Yeah, we'll see certain rules to simplify your grammar. So you will see simplification of CFG. So we will define all these terms. We will recall what we mean by leftmost derivation, ambiguous grammar, and simplification, and all, as and when we look at the problems of that kind. So so we will learn these definitions and all while we're solving the problem. So let's start with the examples. Okay, so here you are given a CFG which looks like this. You have two non-terminals here, which is you have three non-terminals. You have E, T, and F, and you have three terminals, which is this opening bracket, closing bracket, and A. And you have addition and multiplication, and that is the set of variables. This is the set of terminals, and the start state is E. Okay, and these are the production rules. So with that, we want to tell what is the leftmost derivation and rightmost derivation for the string. So what do we mean by the leftmost derivation? So let's say you start with some let's say, for example, that you start with a symbol you want to derive for, let's say, 0 1 1 0, and let's say the production is S0 S0. Then what you do is you have two choices at this point. So S0, you have two choices at this point. Either you can start expanding on this S, or you can start expanding on this S. So if you choose the leftmost one, then what you would do is you will do something like 0 1 S or something, whatever the rules is. And then you have two variables again. You have one S here and one S here. Again you choose the leftmost one. So if throughout the derivation, if you always choose the leftmost non-terminal to expand on, then the derivation is called leftmost. And you can have a symmetric definition where instead of leftmost, every time you are expanding on the rightmost non-terminal, so that would be the rightmost derivation. So we will this will get clear as we do the example. Okay, so let's take the first example. So you have a string which is a plus a plus a, and we want to do the leftmost derivation for this. So how do we do that? You start with e, and let's say e gives e plus t, and so I'll just use red color for the terminals. Okay, then you have two variables that are alive at this point. One is e and one is t. But since we're doing the leftmost derivation, what we will do is we will pick the leftmost non-terminal, which is e in this case. So again we will apply e plus t. Okay, now this somewhat looks like what we want. We want a plus a, and what we have is e plus t plus t. So what we want to do is we want to replace each of the non-terminals with a. So that's what we will do. So but again there are three non-terminals at this point, two t's and one e. So which one we will expand? The one which is on the which is the leftmost. So that is e in this case. So we look at e, and e gives t. Again there are three variables that are alive, so again we'll expand on this t. So t gives f. Again f is a variable, so we'll look at the rule for f, which says f gives a. So we will say f gives a. In this case it is a terminal, so I will so I'm just highlighting it with the red color. So now so now there are two variables that are alive. One is a copy of t here, and one is another copy of t here. Which one we will choose? The leftmost one again. So again we use this production, which is t gives f. So we'll write t gives f. Again f is a non-terminal, so we will do f gives a. So f gives a. So now we have converted another non-terminal into a terminal. Now there is one final non-terminal that is there, and we will do the same process for it. So t gives f, and so t gives f and f gives a. So now all the leaves have terminals at the end. So if we read this string, so if we read this string, it will be a plus a plus a. That is what we wanted. So this is a leftmost derivation tree. This is the leftmost tree for it. So we can write this in terms of we can write this in terms of the derivations also. So how do we do that? First of all, e gives e plus t. Then we will replace the leftmost t with e plus t. Okay, so this is the e that we replaced. Then this is the leftmost symbol, so we will replace it with t. So you have t plus t plus t. Then this is again the leftmost symbol, so we do f plus t plus t. Again f we replace with a, so you have a plus t plus t. Now at this point, t is the leftmost symbol, so what we will do is we will expand on that. So this gives a plus f plus t. This gives a plus t. Then you have only one variable left, which is the leftmost variable. So you have a plus f, and again this gives a plus a. So in this case we expanded on this, then this, and this. So this is the so that's why you have that e derives a plus a plus a. Okay, so so this is the leftmost derivation for the string a plus a plus a. So what we have written here, this is the leftmost derivation for a plus a plus a. So what we did here is that we basically looked at the parse tree and we are just expanding each rule one at a time. Yeah, like this. So then eventually you get the string a plus a plus a. Okay, so let's do rightmost derivation for the same string. So I'll get this copy here. Okay, so okay, so again you have e gives e plus t, and now since we're doing the rightmost derivation, what is the rightmost non-terminal? Here it is t, so we will do t gives f and f gives a, and now there is only one non-terminal that is remaining, which is e. So now we will expand on e. So e gives e plus t. Now again there are two variables that are alive, but t is the leftmost one, so we will expand on that. So t gives f, then f gives a. Then now there is only one variable that is remaining, which is e. So what we will do is e gives t and t gives f and f gives a. So yeah, so that's how we get the string a plus a plus a finally. So we will write the derivation for this. So rightmost so he gives e plus t, then that gives e plus t. So t is the leftmost rightmost symbol here, so we will expand on that. So this becomes e plus t plus f. Then f is the rightmost symbol here, so we will expand on that. That gives e plus t plus a. Now the rightmost non-terminal is t, so we will expand on that. So e gives e plus f plus a. Again f is the rightmost non-terminal, so we will do e plus a plus a. Now again e is the this copy of e is the rightmost non-terminal that we have, so we will do e. This gives t plus a. Then again t is the rightmost variable, so f plus a, and finally f gives a. So this is a plus a, and that is how you derive a plus a plus a. So yeah, so if this makes sense, okay, I'll let you stare at this for a minute. And yeah, basically the whole idea is in the leftmost derivation, every time we have to substitute for the leftmost non-terminal, and for the rightmost derivation you have to substitute for the rightmost non-terminal every time in every step. So it turns out that these are equivalent. So if you have a rightmost derivation, you can also have a leftmost derivation for the string, and vice versa. So yeah, so that is the idea. So if that is clear, then I'll you can take a couple of minutes and try to write CFG for this part B, which is you have two opening brackets, then you have A, and then you have two closing brackets. So you can take a couple of minutes and feel free to pause the video and try it out. We will discuss this in a minute. Okay. Okay. So let's see for the second string, which is two opening brackets, a followed by two closing brackets. So how do we do that? Let's do the leftmost derivation first. I'll start it from here. So I'll draw the parse tree first. So from E, let's say you go to T, then you look at the production for T, and let's say you take F. So you have T gives F. Then you look at the production for F, and let's say you take the first one, which is opening bracket, closing bracket, and E. So now you want to generate this string, and it looks like what we've achieved is we have gotten this part and we have gotten this part. Now in the middle we want E to generate this. So that is the idea. So how do we do that? Again, we will follow the same steps. Let's say E gives, sorry, so I'll write this with red color. Okay, so let's say now E gives T and T gives F again, and it's the same steps that we did, and this time also F gives an opening bracket, a closing bracket, and E. Now we have achieved this part and this part, and we just want E to give us A now. So how do we do that? So what we will do is we will say E gives T, T gives F, and this time F gives A. Okay, so yeah, so let's write, this is the parse tree that we've written. Let's write the leftmost derivation corresponding to it. So how does it look like? So E gives T, T gives F, F gives opening bracket, E closing bracket, then E gives T, sorry, E gives T, T gives F, F gives another set of opening bracket, then E gives T, T gives F, and this time F gives A. And this is the string that we wanted. So E derives A. That is the string that we wanted. Now one thing to observe here, if you try to write the rightmost derivation for this, you will end up in exactly the same tree that we have here, even for the rightmost derivation, and the same set of derivations for that string. Why is that? Because if you look at the entire series of derivation, at any point in the tree there is only one non-terminal. So to begin with, you had T, then T was replaced with E was replaced with T, so there is only one non-terminal. Then T gets replaced with F, so there is only one non-terminal, and then F gets replaced with this opening bracket, E, and closing bracket. Again you have only one non-terminal. Then the same set of steps repeat, and again E is the only non-terminal. Then E gets replaced with T, T gets replaced with F, and finally F gets replaced with a terminal. But in the entire tree of derivations, there is only one variable at a time. So it would be, so that since there is only one variable, the leftmost variable is the same as the rightmost variable. So if you do the rightmost derivation, you will end up in the same thing. And rightmost derivation, so it would end up being the same because there is only one variable. So for both of them you will get the same answer. So yeah, that's basically the idea of rightmost and leftmost derivations. So if you're comfortable with that, we will move on to the next question. So here you are given the following grammar. So this is a CFG, and this is the CFG, and there are two rules. So what is the set of variables here? So set of terminals here is A, B, epsilon, and the set of variables here, yeah, and the set of variables here is S, Y, that's it. So you have two variables. So given that, what you want to do is, there are two questions. One is that you want to describe what is this language. So you can either write it mathematically or you can just describe in words. Okay, so that is the first part. Second part is you want to give context-free grammar for its complement. So I'll wait for a minute or if you're watching it online, you can pause the video and think about it, and we will discuss. Okay, so let's see. um, okay, so let's look at this step by step. So S gives, there are three derivations at this point. So S gives A as B, or by, or ya. So let's look at what all can you generate from S if you look at A as B. So here you have S gives A as B, and then let's say you go, like, you can apply the same rule like couple of times, and eventually when you have done that, finally, in order to terminate, this will either take a by or it will take a ya. So we will look at that in cases. Now once you get to y, what can y generate? So y gives by, or ay, or epsilon. Okay, so y can give you a bunch of a's, or it can give you a bunch of b's. So the language of y that is generated here is nothing but a plus b star. Okay, so this is what the y can generate, because you can, the next symbol that you can produce could be a b, or it could be an a. If you want an a, then you use this. If you want a b, then you use this, and you can do it as many times as you want, and eventually when you're done with the string that you wanted to generate, you can just replace the y with epsilon. So this y is capable of generating everything. Okay, so that's what will happen. So if you end up taking this, you will end up generating a plus b star here. So what is the yeah, so what is the um yeah, what is the language, what are the strings that you have generated by this process? So strings that you have generated is a to the k, b to the k. This comes from taking k copies of asb and b, asb, and then when you finally replace this, you will either get b followed by a plus b star, or if instead of this, at this point, if you take s gives s gives ya, then again you do all possible derivations here, ba, whatever. So again this y is capable of generating anything. So this gives a plus b star. So in that case you get a plus b star followed by a. Okay, so this is nothing but a to the k, a plus b plus followed by b to the k. So basically this is capable of generating everything. This is generating, so if you take s gives a as b, then you can generate any string that starts with a and ends with b. Okay, so that is the first kind of strings that you have. So if so if you call this L1 is the set of all x such that x starts with a and ends with b. So this is definitely generated by the grammar that we have. Now let's see what happens if you don't take this a as b, but instead you directly take by. So let's see what happens in that case. So s gives by. Okay, I'll maybe take a new page. Yeah, so in this case s gives by, and then like we said earlier, y is capable of generating every possible string here. So yeah, so here you can have all possible a plus b star. So what is the language? L2 is the set of all x such that x starts with b. Similarly, if instead of by, if you look at the third production, so sorry, yeah, instead of taking by, you take ya, then what you get is s gives y a, and then y again, like we said, y can give you every possible string. This is a plus b star. So what is the language? L3 is x such that x ends with a. So L is L1 union L2 union L3. These are all the possible strings. So what is that? That is x such that x starts with a, starts with b, union x such that x ends with b, with a. So union x such that x starts with a and ends with b. Okay, so this is generating all possible strings, because look at any string of length at least one, it will either start with a, it will either start with b or it will start with a. So if it starts with b, then it is already generated by this, it is already taken care of by L2. L2 generates this. Then then you look at the strings that start with a. Then there are two possibilities: it starts with a and it ends with b, or it starts with a and it ends with a. So if it ends with a, then L3 is the language that takes care of this. So L2 generates this. This is generated by L3, and the only thing that is left is the set of strings here that start with a and end with b. But these are exactly the strings that are generated by L1. So all these strings are generated. The only thing, so the given CFG generates all strings of length at least one. Okay, note that a and b are also generated. So how do we get a? So in order to get a, what you do is s gives y a, then y gives epsilon. So if you do this, you will generate a. Similarly, for generating b, you do s gives by and y gives epsilon, then you would have generated a b. So basically you can generate all possible strings. Only thing is, we want to see, can we generate epsilon? So let's see that. So note that s either gives a as b, or it gives a by, or it gives a ya. In either case, it is giving you at least one non-terminal. So even if y, let's say, later on gives you epsilon, even if that happens, you have generated at least one letter in the string. So you cannot generate epsilon using this grammar. So note that epsilon is not an element, cannot be derived. Observe that epsilon cannot be derived from the given CFG. Okay, so that means, what is the language? So language of this grammar is a plus b plus, which is all the strings of length at least one. So this would be a b, a b, b a b b, then a and so on. So this is the language of the given grammar. So yeah. So if that is clear, can then we the second part of the first part of the question says you want to identify what is the language of the grammar, and that is what we precisely did. So we said that this is the grammar of the given language. That is the first part. Now we are asking, what is the grammar for the L of G complement? So let's see what is L of G complement. L of G complement is nothing but complement of a plus b plus, which is nothing but epsilon. So how do we give the grammar for that? So what you do is you simply start with the start state and produce epsilon. That's it. So this grammar only generates epsilon, and that's the only string in the language. So this is the answer for part 2. Okay, so yeah, so that is what we did. Basically, we tried to use every possible, so we have given this grammar, we tried to use every possible derivation to see what all strings are there in the language. So we categorize this. If you use the first rule, which is ASP, then you will generate L1, which is all the strings that start with A and end with B. Then if you use the second rule, then we said if you use by, and then y generates every possible string, so you end up getting all the strings that start with b. Similarly, if you use the third rule, which is ya, s gives ya, then you have that it generates L3, which is all the strings that end with a. Then we said that okay, L can generate L1, it can generate the strings in L2, and it can generate the strings in L3. So we observed using the simple English definition that it basically generates all the strings of length at least 1. Then the only question was that of epsilon. So we looked at epsilon, and we observed that epsilon cannot be generated. So then this is the language that we got. So we got L of g is equal to a plus b plus, and then using that we got a language for the complement of the language, and we simply wrote a grammar for it. So those were the two parts. One was generating identifying the language, the other was generating the context free grammar. So I hope that was clear. So if that is the case, I'll move on to the next question. So yeah, so here you are given you're given a grammar, and the words that are written inside this angular brackets and in capital, such as sentence, these are the variables, and the words that are written in small letters, such as if, such as the, and so on, these are the non-terminals. These are the terminals. Okay, so given that, what you are asked to do is you've been given the string, which says, so this is the string that you have. I'll underline it in red. So this is the string that you have. Okay, the girl touches the boy with the flower. So this is the string that you have, and what you're asked to do is you're going to write a derivation tree for this, the parse tree for this, and you will see that there are two leftmost derivations for the same sentence that are possible. So there is no unique leftmost derivation in this case. Okay, so I'll wait for 2 minutes for you to try. If you need more time, then please feel free to pause the video whenever you're watching it. So I'll wait for 2 minutes, and then we will discuss. What you have to do is, for the given string, which is the girl touches the boy with the flower, you have to write two different leftmost derivations for the same string using the given grammar. Okay, so yeah, let's see. Just a minute. Oh, so let's see how to do that. Okay, so you are going to start with the sentence. So that is the first thing. So sentence is the start variable, so we're going to start with it. Then what we will do is it has only one rule. So what is the rule? The rule is that sentence gives noun phrase followed by a verb phrase. So that is what we will write. So we will write, yeah, so we will write that sentence gives noun phrase followed by verb phrase. Okay, then let's look at the noun phrase. What does the noun phrase do? Noun phrase, okay, so since we are doing leftmost derivation, we are going to expand on this. So what does noun phrase do? It either gives you a complex noun or it gives you a complex noun followed by a preposition. So yeah, so let's say that noun phrase gives a complex noun. Let's look at that complex noun. And again you have two variables at this point. What are the variables? One is the complex noun, the other is the verb phrase. But we are going to do the leftmost derivation, so we are going to have to expand on this. So let's look at what is the complex noun do. Complex noun simply gives you article followed by noun. So let's write that. So this is going to give us article followed by noun. And then you have three variables at this point. You have article, you have noun, and you have verb phrase. So what we will do is, since we're doing leftmost derivation, again we will expand on the article. So let's see what article gives. Article gives a or it gives the. So let's say we take the. So I'll write the terminals in red color. So you have the. Then what are the variables at this point? You have noun, you have verb phrase. What is the leftmost one? It is noun. So we will expand on noun. So what does noun give? Noun can give a boy, girl, or flower. So let's say we take girl. Okay, so now there is only one variable at this point, which is verb phrase. So we will expand on that. What does verb phrase give? Verb phrase gives us a complex verb, or it gives, yeah, or it gives a complex verb followed by a preposition phrase. So let's suppose it gives it takes the second rule, which is complex verb followed by preposition phrase. So then there are two variables at this point. What are they? One is the complex verb, the other is the preposition phrase. So again the leftmost one is complex verb, so let's expand on that. What does complex verb give? It either gives you a verb or it gives you a verb followed by noun phrase. So let's say it takes the second one. It says verb followed by noun phrase. Now there are three variables. One is verb, the other is noun phrase, the other is prep phrase. So again we will expand on the leftmost one, which is verb. So verb says it is touches, likes, or sees. So let's say we take touches. So you have touches. Now there are only two variables. One is noun phrase, the other is preposition phrase, and we will expand on noun because it is the leftmost one. So let's look at the noun phrase. Noun phrase gives you a complex noun, or it gives you a complex noun followed by a preposition phrase. So what we will do is, we will let's say we will take the first one, which is complex noun. So noun gives complex noun. Now again you have two variables, one is this and the other is this. So the leftmost is complex noun, so we will expand on that. So complex noun gives article followed by noun. So you have article, then you have noun. So let's look at article. What does article give? It gives a or it gives the. So in this case we will take the and we will write it in red because it is a terminal. Similarly, if we look at noun, then there are three choices. It is boy, girl or flower. So let's take boy. So what we have, the strings, the partial string that we have generated at this point is reads like this: the girl touches the boy. Now what we want is, we want to write with the flower. And what is the variable we have? The variable is prep phrase. So we will look at the rule corresponding to that. So what is the rule corresponding to prep phrase? So this is a typo here, this should have been phrase. So the prep phrase, preposition phrase gives a preposition followed by complex noun. There is only one rule, so there is no choice, so we will write that. So there is preposition followed by complex noun. Okay, so now there are two variables, one is the preposition, the other is the complex noun, and we will expand on preposition because it is the leftmost. So what does preposition tell you? There is only one choice, it is with, and it is a terminal, so I'll write this in red. So this is with. Now we're getting there, we've almost generated the string. The only thing that is remaining is to expand on complex noun. So what does complex noun give? It gives article followed by noun. So there is no choice, so we will write it as it is. We will write article followed by noun. Okay, so now we're almost done. So the leftmost one is article. What does article give? It gives a or the. Let's say we take the, so this gives the. Now there is only one non-terminal, that is noun. So what does noun give? Noun gives boy, girl or flower. So I'll write flower. So what is the string that we generated? Let me write that. The string that we generated is, the girl touches the boy with the flower. That is the string that we generated. And what did we do? We did leftmost derivation. This is what we did, and we got the string. Okay, so yeah, so now what we are going to do is, for the same string using the same grammar, we are going to generate a different parse tree, a different leftmost derivation. So let us do that. So to do that, I'll just copy this on the next page, and then we will freshly do another leftmost derivation. So I'll get copy and I'll paste this here, and I hope this size is visible. Okay, so this is what you have, and yeah, and we're going to do the same thing but with a difference this time. So some part of it is same. You start with sentence, then okay, maybe this time, okay, let's keep it that way. So you start with sentence, then sentence gives noun phrase followed by verb phrase, then let's say that we are at noun phrase, and noun phrase gives you complex noun. Let's say, suppose this gives complex noun, and again this is the leftmost derivation. So we will look at complex noun. Complex noun simply gives article followed by noun, so we will do that, article followed by noun. Then we look at the article. Article is a or the, so let's say we take the, then you look at noun. and let's say you take boy, so sorry, let's say you take girl. Okay, now let's look at the variable that is remaining, that is only verb phrase. There is only one variable, so we will expand on that. So what does verb phrase give? It gives a complex verb. Okay, just a second. Okay, so let's say that we take this verb phrase which gives, where is verb phrase, yeah, so let's say verb phrase gives complex verb. So you have complex verb. Then let's look at complex verb. So complex verb gives verb or verb followed by noun phrase. So let's say it gives verb followed by noun phrase. Then you have the leftmost variable is verb, so we will expand on that. So verb either gives you touches, likes, or sees. So let's say we take touches. Then you have only one variable that is remaining, that is noun phrase. So we will expand on that. So noun phrase is it gives you complex noun, or it gives you complex noun followed by preposition phrase. So we will look at this derivation. So this gives complex noun followed by preposition phrase. Then the leftmost variable at this point is complex noun. So let's look at complex noun. It gives you article followed by noun. So we will simply write that. It gives article followed by noun. And again, article can give you either a or the. So let's say we go the. Then you have noun which gives boy, girl, or flower. So let's say it gives boy. Then the only variable remaining at this point is prep phrase. So we have to expand on that. So prep phrase gives you preposition followed by complex noun. So what we will do is we will write that. So this gives preposition followed by complex noun. Then the leftmost one is preposition, so we will expand on that. Preposition only has with, so we will write with. Now we have complex noun, and for complex noun it simply gives you article followed by noun, so that is what we will write. So this is article followed by noun, and in this case from the article we will choose the, and from the noun we will choose flower. So what is the string that we generated? We generated the girl touches the boy with the flower. Okay, so what I'll do now is I'll get both these parse trees side by side so that we can see that they are not the same. They are both leftmost derivations that generate the same string, but they are different. So let's see that. I'll get this both on the same page now. So I'll take this, sorry. So this is the first one and this is the second one. So I'll try to get this. Okay, So I'll draw a line to separate the two so that there is no confusion. So this is the first grammar, the first leftmost derivation, and this is the second leftmost derivation. So we have both of them side by side. Now let's see, are they really different? So where are, if they are, then where are they different? So let's try to read the tree starting from the root. So the starting is same, both start at sentence. Then the left subtree here is exactly the same as left subtree here. So noun phrase part is exactly the same. Then let's look at the right side of the tree. So you have verb phrase here and verb phrase here. But now at this point you have that complex verb phrase gives complex verb followed by preposition phrase, and in this case you have that verb phrase gives complex verb, and then the entire right part of the subtree is different. So let me point out where the difference happens. So the difference happens from this point. So this part is different from this part because we use different rules, but we still got the same languages. So if it is the case that if there is a string such that there are two different leftmost derivations using given grammar, then you say that then the grammar is what is called ambiguous. So then you call it ambiguous. So ideally what we want is, we want a single, for every possible string we want to have a single possible leftmost derivation. We don't want like lots of possibilities. So if there is a string for which the given grammar has two or more different possible left tree derivations, then you say that it is ambiguous. So it is not uniquely derivable, and we call it to be ambiguous. Okay, so it is possible that for some grammars, for some languages, we can modify the grammar so that the ambiguity is removed. It is possible in some cases, but in some cases it is not possible. So if it is not possible, then you say that the grammar is inherently, that the language is. So in some cases it is possible to remove the ambiguity in the grammar. Okay, but for some grammars we cannot remove ambiguity. What do we mean by that? It means that for that language, that is for language L, every grammar for L is ambiguous. Then in that case we say that the language is ambiguous, or it is also sometimes called inherently ambiguous. So what that means is, no matter what you do, no matter how you write the grammar for that language, it will always be ambiguous. Then in those cases you say that it is inherently ambiguous. So if there is time, we will look at examples of this kind. We will try to look at examples of both kind, one where it is possible to remove ambiguity, and one where it is not possible to remove ambiguity. So we'll try to look at examples of this kind. So okay, so what is the takeaway from this example? It was just an exercise to see that okay, here is a grammar for which the particular string that is given has two leftmost possible derivations. So in terms of English, what does this mean? If you look at the first grammar, then what that means is that the girl, which is the subject in this case, uh, yeah, yeah, in this case what it means is that the girl touches the boy with the flower. So the flower is an object with which she touches the boy. But in the second case, the meaning is different. So in the second case, what is the meaning? It says that the girl touches the boy who is holding a flower. So so the meaning of the English sentence that we derived is different in both the cases. In the first, the flower is the object with which the action is being taken, and in the other case, we are describing the boy as if he is holding the flower. So yeah, so in that sense also the sentence is ambiguous because it can be interpreted in two different ways, and that's what this context free grammar example kind of illustrates. So yeah, so that is the yeah, so yeah, that was basically an illustrative example to connect with the English that I mean that we speak. So okay, so yeah, that was the takeaway. And yeah, I'll move on to the next question. So yeah, so now that you know what is an ambiguous grammar, let's see, I'll wait for a minute. You can check whether the given language is ambiguous. So what is the language? The language is the set of all strings of the form a to the I, b to the j, c to the k, such that either the number of a's is equal to number of b's or number of b is equal to number of c. For example, a b b c, this would be in the language. Then a b b b c c c, this would be in the language. But or also a b c would be in the language, and so on. But strings like a b b c would not be in the language, because number of a's is not equal to number of b's, and number of b's is also not equal to the number of c's, so this is not in the language. So that's basically what the given language is. So you want to tell whether it is ambiguous or not. So I'll wait for some time, you can think about it. Okay, so let's see what are the answers. Okay, I'll erase this part. Okay, so let's see, let's try to write grammar for this. So you can think of A as follows. This is set of all a to the I, b to the j, c to the k, such that I equals j or j equals k and I, j, k are greater than equal to 0. So you can think of this as A set of all a to the I, b to the j, c to the k such that I is equal to j union set of all a to the I, b to the j, c to the k such that j is equal to k and I, j, k is at least 0. So this is basically because there is an OR condition here. You can just break this into two different languages. So what we will do is we will independently try to design a CFG for this, and we will independently try to design a CFG for this. So let's say that I can somehow get a grammar for this, which is G1, and I can somehow get a CFG for this is G2, and let's say the start variable for this is A1, or let's say S1, V1, P1 and T1, and then you have S2, V2, P2 and T2. Then if I have a grammar for this, I can simply do one step and get a grammar for A. So how do I get a grammar for A? So let's say grammar for A is S, V, P, T. Then what you do is simply write S gives S1 or S2, and T would be your T1 union T2. Yeah, T would be T1 union T2, P yeah, and yeah, and V would be V1 union V2, and the set of productions would be P1 union P2 union this one particular string that we wrote. So it would be S gives S1 or S2. So this all together gives you the grammar for A. That's the whole idea, because from S you can either get to S1, which in that case you will be generating this, or from S if you go to S2 then you will be generating this. So in either case you are able to generate the entire language. So hence A would be so hence S would be able to generate the entire language. That is what we wanted. Okay, so our goal now is to generate a grammar for this part and for this part. So let's do it step by step. So our task reduces to generating grammars for grammars G1 and G2. Okay, so let's do that one by one. So I'll take a new page. So the first language that we had, I'll call this A1, is set of all A to the I, B to the J, C to the K such that I is equal to J and I, J, K is at least 0. So let's see how to do that. So yeah, so the idea is, let's say you start with S1, then you go to A followed by B, and what does A do? A is responsible for generating equal number of A's and equal number of B's, and eventually it gives you epsilon. And what does B do? B is just responsible for generating any number of C's. So you have CB or epsilon. So what we did is we broke this into two parts. We thought of this as A's and B's, and here you have C's. So the part A is going to generate equal number of A's and equal number of B's, and the part B is going to generate any number of C's. So that is what we did. So yeah, so that's basically your grammar for A1. That's basically it. Now similarly, let's say you have A2, which is A to the I. Also, like, note that because we have epsilon here, the boundary conditions are matched. That means you can simply generate AB, or you can generate epsilon, or you can generate C. How do you get epsilon? So S1 gives AB, then A gives epsilon and B gives epsilon, so that way you can generate epsilon. So basically the variables are such that the boundary conditions are matched. Then let's look at A2. Yeah, so this is your G1, and let's look at A2. Okay, so this is A2 and we want to write grammar for this. So what we will do is S2 gives, let's say, CD, and C is responsible for generating any number of A's, and D is responsible for matching the number of B's and C's. So how do you do? B, D, C followed by epsilon. So this D part will generate equal number of B's and equal number of C's, whereas C could generate any number of A's. So that is the grammar for G2. So now, like we said, we just want to combine this together. So how will we do that? So what is the final grammar? The final grammar is S gives S1 or S2, then S1 gives AB, A gives AAB or epsilon, B gives CB or epsilon, then S2 gives CD, C gives AC or epsilon, and D gives BDC or epsilon, and that is basically the grammar for A. Yeah, so yeah, that's basically the answer. So the second question that is there is this ambiguous? So what do we mean by that? Is there some string over A's and B's that we can write, which can be generated in two different leftmost derivations? So I'll wait for some time and let you think. Feel free to pause the video and think about it. Okay, and then we will discuss. Okay, so let's discuss. So I'll try to get this thing on a new page. So I'll paste this. So yeah, let's look at the answer. So let's say I want to generate the string epsilon. Okay, so let's see how we can do that. So S gives S1, then maybe S1 gives AB, then from A we know there is a production that takes us to epsilon, so I'll write an epsilon here. From B there is a production that takes us to epsilon, so we will take that one. So from B we get to epsilon, and basically the string that we have generated is epsilon, which is nothing but epsilon. Now let's see how we can generate the same thing in different way. So let's say you start with S, but instead of S1, let's say you take S2 this time. Now what is S2 give? S2 gives you CD. So let's write that. So S2 gives you CD. Then from C you can go to epsilon. So let's say you take that production, and similarly from D you can go to epsilon. So from D you go to epsilon. So what is the string that we generated? We generated epsilon, which is nothing but epsilon. So we generated the same string, but there are two different leftmost derivations. So in this case S1 gives S2, in this case S1 gives S gives S2. So the derivations are different. So two different leftmost derivations for epsilon. Or if you don't want to do with epsilon, you can maybe take a different example. So let's see. So let's see how to do that. So maybe I want to generate the string ABC. Let's see how we can do that. So you are at S, let's say you take S1. From S1 there is no choice, so you go AB. Then from A, let's say you take this, you take the first rule, which is A gives AB, and then again the leftmost variable at this point is A. So let's say you take A gives epsilon. So you have A gives epsilon. Then let's say you take B, and B basically gives you C followed by B. So let's say, okay, so this gives you small c followed by B. And then let's say you say B gives, okay, I'll write this in red so that there's no confusion. So this is A, B, C, and then B gives epsilon. So what is the string that we generated? We have epsilon B, C, epsilon, which is nothing but A, B, C. Let's see how we can do this in a different way. So let's say S gives S2, then yeah, let's say S gives S2, then S2 gives you CD, which is what we have here, then C gives AC. So you have AC, and then the leftmost variable that we have is C. So let's say we take this production that C gives epsilon. So you have C gives epsilon. Then the only variable that we have is D. So let's look at D. Let's say D gives B, D, C. So you have B, D, C. Now let's say the second time D gives us epsilon. So what do you get? You get D gives epsilon. So what is the string? It is A epsilon B epsilon C, which is ABC. So again, we have two different derivations for the string ABC, but the past trees are different, or the leftmost derivations are different. So hence again, this is yet another example to show that G is ambiguous. Okay. So that is basically the given example. So what we did was we generated a grammar for this language, and we showed that the grammar that we generated is ambiguous. We haven't yet shown that the language is ambiguous. All we said that the grammar that we generated is ambiguous. So if there is time, we will look at how to show that the grammar is indeed the language is inherently ambiguous. So that is not what we showed now, but if there is time, we will see that. Okay, so if that is clear, maybe so maybe then we can try. Sorry, just a minute. Sorry. Okay, so I'll get back to these questions, but for now. I'm not sorry. Yeah, sorry, just a second. Okay, so yeah, so there are a couple of more questions, but yeah, if there is time, then we will come back to this. um, yeah, so what I'll do is I'll take a different question now. Okay, so I'll come back to these questions, but let's say yeah, so let's do what is called simplification of grammar. Okay, so what do we mean by that? So generally we want our grammar to be in a certain form. We will look at that next time, but there are certain kinds of productions that we can remove so that the grammar is simplified. So okay, so there are so the kind of moves that go like let's say b gives epsilon in this case. So if there is some variable that produces epsilon, then you call that it is an epsilon rule. So any rule of the form alpha gives epsilon, this is called an epsilon rule. And what we want to do is we want to remove it. So there are reasons why we want to do that. We will look into it later, but for now let's see how to do that. Okay, so in this case there is one epsilon rule, which is b gives epsilon, so we want to remove that. So how will we do that? Simply, so let's say s0 gives s gives asa or ab, a gives b or s. So now we are okay with b giving b, but we want to remove b gives epsilon. So what we will do is we will replace every occurrence of b with an epsilon. So let's see where. Here you have a gives b. So what you can do is when a gives b, and if b is replaced with epsilon, then it is same as saying that a gives epsilon. So what we will do is we will write, this is the modified grammar, so b gives b, in this case you had epsilon. So now we have removed epsilon. What we will do is we will say a gives b or s or epsilon. In case of s, there is one occurrence of b, which is here, and there is occurrences of yeah, so we want to replace it with every possible yeah, so a gives b, or if b is replaced with epsilon, then a b goes to a epsilon, which is nothing but a, so we will simply write a. And then s0 gives s, so there is no occurrence of b, so there is nothing that we need to change. So that is what we did. Now in the resulting grammar, which is this box, now in this grammar there is one new epsilon there is new epsilon rule. There is, we have removed b gives epsilon, that is no longer there, but there is a new epsilon rule, which is a gives epsilon. So what we want to do is we want to do something similar and get rid of this epsilon rule. So let's see how to do that. So the set of steps is similar. Now what you do is you have b gives b, you have a gives b or s, because a gives epsilon is what we want to remove. So now you have s gives asa or ab or a. But let's look at this. S gives asa. What if this occurrence of a is replaced with epsilon? Then you get sa. But if this occurrence of a is replaced with epsilon, then you get as. And if both are replaced with epsilon, then you get nothing but s. So what we will do is we will simply replace it with all the three possibilities. So here we have or as or sa or s, and then s0 gives s, that is the same as earlier. So that's the only change that we made. So now with this we have the grammar that we had earlier is the same as, I mean the language remains the same, but we have gotten rid of the transition of the form a gives epsilon. So what we have done is we have removed what are called epsilon rules. So basically the idea is whenever you see an epsilon rule, we are going to repeat this process as many times as you see epsilon rules. We will keep on repeating. Ultimately at the end we will get a grammar where there is no epsilon rule. So this is what happened. In this case we had to do it 2 times. In general it may be required to do more times, but at the end you will eventually have the grammar that looks like this. So you have no epsilon rule. Okay, so yeah, that was one kind of simplification. Let's see what other things are there. Okay, so let's see what are the other things. So let's define what is called unit rules. What we mean by unit rules is maybe I'll take a new page and write there. Okay, so what do we mean by this? So as the name itself suggests, it has something to do with one non-terminal being there. So let's say s gives a. So in this case, on the right hand side there is only one non-terminal, so this is called unit rule. This is not what we want. So this is not what we want. But let's say on this side you have ab, or you have that a gives bcd, or a gives a. These are not unit rules. Why is that? Because you have 2 variables, 3 variables on this side, which is clearly more than one. So this is not unit rules, because more than one non-terminals on RHS. Okay, but what about this? Is this a unit rule? No, because in this case you have only one thing on the right hand side, but it is not a it is a terminal. So this is a terminal. So hence this is also not a unit rule. So whenever we say unit rule, the idea is that on the right hand side you have only one non-terminal. So for example, something like s gives a p b, this is also a non-terminal, this is also a unit rule, because there is only one non-terminal. So these are not the kind of rules that we want. These are not desirable, so we are going to eliminate. So why is this not desirable? And all of this we will see later, and maybe in the coming week, when we look at CYK grammar. Maybe we'll try to see some intuition, but right now all we want to do is, if there are unit rules like this, we just want to eliminate them and get rid of them. So let's see how to do that. In this case, can you identify what are the unit rules? So let's look at this. B gives B. This is not a unit rule because this is a terminal. But A gives B, this is a unit rule. A gives S, this is a unit rule. Before that, S here gives so S here gives S, this is a unit rule. and S0 gives an S, that is also unit rule. So one by one we will just try to eliminate them. So how do we do that? Okay, so let's do S gives let's look at this. S0 gives S, then you have S gives ASA or AB or A or SA or AS or S, and A gives B or S, and B gives B. So what does it even mean to say that S gives S? Then you can use other derivations, other rules for S, but yeah, but uh, does it even make sense to say S gives S? Because whatever whatever is written after this, A B C or whatever, that we could have simply replaced at this stage only. So you could have simply written S gives ABC instead of doing it that S gives S and then S gives ABC. So this is basically not adding anything. It's like redundant to your rules, so it's safe to eliminate it. So what we will do is we will simply eliminate this S. So this is the new grammar that we have. So this is eliminated S gives S. Okay, now there is one more unit rule that we have. I mean, there are more, but what we're looking at is this: S0 gives S. This is a unit rule because on the right hand side there is only one non-terminal. Okay, so what we will do is we will eliminate that. So let's see how to do that. So what we are saying is S0 gives S, then S may have like a bunch of options from whatever is here. Okay, so why do we even need this first step? You can simply start with S. So what you do is you simply eliminate this rule and say S gives, S0 gives, or yeah, sorry, you simply say S gives ASA or AB or A or SA or AS, and A gives B or S, and B gives B. So this is your new grammar where S0 is completely eliminated and S is your new start symbol. Okay, so what we have done is we have maintained that the grammar remains the same, but we have gotten rid of this sort of S0 gives S. So what we have done is we have eliminated S0 gives S. Okay, so yeah, so that was it. So even now we have not completely removed all the unit rules. There are still more unit rules. So A gives B, A gives S, these are unit rules, and we will eliminate that. So let's see. Yeah, so let's see how to do that. So here you are given a grammar, and the unit rule is A gives B. So we will try to get rid of it. So yeah. Okay, and now we want to get rid of A gives B. So what we will do is everywhere whenever there is an occurrence of A, we will replace it with B as well. So yeah, so what you can have here is you can have BSA, or you can have so I'll write this in new color, in a different color. So you can have BSA or ASB, or you can have BSB, or you can have there is the next occurrence is here, so you can have SB, or you can have BS. Yeah, and similarly you do the same thing here. So here, yeah, so here also you get BSA or ASB or BSB or SB or BS, and that is how we have eliminated A gives B. So similarly you can do the same steps. In this case now we still have one more unit production, which is A gives S. So you can do the same steps, basically replace every occurrence of A with S, and yeah, and that is how you will get we will have removed this unit transition, which is A gives S. So yeah, so I'll not do that now, so I'll move on to a new question. Yeah, so the whole point of this was we saw how to eliminate what are called unit productions, which is alpha gives epsilon, and we've seen how to remove what is called unit production. So we will see where this this will be useful later on, so let's keep it at the back of your mind. We will see later how to use it. Okay, so okay, so I think we have some time to do one more question. So let's see, let's look at this question. So what you are given you're given a CFG, you're given a language. So let's say L is equal to the following language, where you have equal number of A's and equal number of B's. So it could be A B A B, but it could also be A A A, B B B, or A B B A B A. So all of them, so basically they could be in any order, but ultimately if you look at a string, then the total number of A's that are there in the string should be equal to the total number of B's in the string. They could be interspersed yeah, but at the end you want the count to be equal. So that is the language. Okay, and we want to design a context free grammar for it, but at the same time we want that it should be unambiguous. So for any string there should be a single possible leftmost derivation. There should be a unique leftmost derivation for it. So that is the task. I'll wait for 2 minutes. You can think about it, or if you need more time, then please feel free to pause the video and do try to come up with an unambiguous CFG for it. Yeah, so I'll discuss in 2 minutes. I'll wait. Okay, sorry, I think the screen share stopped. I'll share it again. Okay, sorry about the yeah, so yeah, I'll just wait for a minute and start. Okay, so let's see how to do that. Let's just try to come up with something, and then let's see whether it is indeed the grammar and whether it is ambiguous. Okay, so a very naive attempt would be that S gives ASB, and S gives B as A or epsilon. So what if we write this grammar? What happens is that we are, what this is intuitively saying is that when you say A is B, we are saying that if there is an occurrence of A, it should be followed with an occurrence of B somewhere. One for every A, one there should be one B. Similarly, what this says is if you are writing B at this point, there should be an A that comes up later at some point, so that the number of A's and number of B's is balanced. Okay, but this does not quite capture all the strings, because what if yeah, what if I want to write a string of this form, maybe a bb. So if you, okay, so let's maybe take a simpler example. If I want to generate the string ab, then can I do that? Let's give it a try. So this should be in the language, so our grammar should be able to generate it. So the grammar that we came up with first is this. Okay, let's see what happens. So S gives A as B, then S gives B as A, and then S gives epsilon. So what is the string that we generated? We generated AB, which is what we wanted. Okay, so it looks like it is generating some strings, but does it generate everything that we wanted? So let's take this other example. Let's say it is ABBA. Now what will happen is S gives A as B, then no matter what you write here, your string is always going to have a B at the end. If you have A in the beginning, then you're going to have a B here, which is not what we want. But if you take S gives B as A, then you get a B, then you get an A at the end, which is what we wanted, but you get a B at the beginning, which is not what we want. So it's somehow that if you're trying to make up for something on the left, you are losing out on the right, and if you're trying to do on the right, then you're losing on the left. So how do we fix that? So I hope it is clear with the example that there are strings that should be generated by the grammar, but it is not generating. So how do we fix that? We'll simply add one more rule. So what is the rule that I'm adding? So the rule I'm adding is S gives A as B, which is as earlier, S gives B as A, which is as earlier, and the one more thing that we have added is S gives SS or epsilon. So let's see how this is fixing our problem. Let's look at the same string that we were not able to generate earlier, so which was ABBA. So how does this work now? Okay, S gives, let's say S gives SS. We tried with this, it was not working. We tried with this, it was not working. So we added one more rule, which is S gives SS. Let's see what happens now. So S gives A as B, and then S gives epsilon, then S gives B as A, and S gives epsilon, and S gives epsilon. So what is the string? The string that we generated is ABBA, which is exactly what we wanted. Okay, let's try some other example. Let's try maybe AB. You have 4 A's at the moment. So I'll write. So how many? Okay, so there are 5 A's and there are 5 B's. Okay, so this is the string that we want. Let's see how we will generate it. So using the grammar that we have. So this is our final grammar. So let's say S gives A as B. Using that, we have generated A here and B at the end. Then again you want an A at the beginning and B at the end, so we will do the same thing. So S gives A as B, then now you have generated A here and B here. This is the string that you want B at the beginning and B at the end. So now what you do is, now you use the third rule, which is S gives SS. Now let's see what happens. So now let's say S gives B S A, and S gives epsilon. So yeah, and for the second S you have, it gives, yeah. So by doing this, we have generated B and A that occurred after A. So B has been generated, we want to generate AB. So how to do that? Now S gives ASB, and that's how we got this A and this B, and we just want to generate BA. So S gives BSA, and S gives epsilon. So then you have B and A. So yeah, that is the string that you have. And this is the grammar. So this is the grammar corresponding to it. So actually what this SS does is, it enables us to take care of the interspersed A's and B's instead of those that just start with A, end with B, or vice versa. SS now sort of empowers us to use this in multiple number of times, so that you can get all sorts of combinations. Now you can convince yourself that this is indeed the grammar that generates all possible strings where the number of A's is equal to number of B's. What we want to additionally show is that this is indeed an ambiguous grammar. So we want to show that this is an ambiguous grammar. So how do we show that? Maybe I think we are almost near uh, 8 p.m. So what I'll do is, I'll let you think about this, and we will discuss this in the upcoming tutorial. So what we've done is, we have given the grammar, which is this is the grammar corresponding to it, and we want to claim that this is an unambiguous grammar, meaning for any string that you give me, there is a unique derivation for it. You cannot have multiple leftmost derivations. So we will see that in the coming week. And so yeah, that is just to recap what we did, just to summarize what we did today. We looked at what is called leftmost derivations, what is called rightmost derivations. Then we saw what is called ambiguous grammar. We saw how to interpret it in different ways, and we haven't seen how to eliminate. I think we saw one example where you can eliminate it, but we did not see examples where it is inherently ambiguous. So maybe we'll look into it in the coming week, and yeah, maybe we'll look into some closure properties as well. So we saw the other thing that we saw was how to simplify grammar. So we saw how to get rid of epsilon rules and how to get rid of the unit transitions. So yeah, that is all we did. So next time we will, there are a couple of questions that I wanted to talk about, but we are running short of time, so I'll take it up in the next week as well. So this part of showing that the grammar is unambiguous, and some more examples, I think we'll do it the next time. So yeah, so I think that is all for today. I'll see you next week from 6 p.m. to 8 p.m. Yeah, that's all for today. Thank you. So I think I'll stop the recording and leave the call.